We covered partial fractions way back at the beginning of the Year 2 pure maths content. When we first looked into it, there wasn't a whole lot that we did with it. We talked a little bit about how it would come in handy for binomial expansion and for integration, but then we left it to one side and we covered lots of other things in between times. We have seen binomial expansion and how it can be helpful to break apart a big complicated looking fraction into pieces that are simple enough that you can expand them using the binomial expansion formula. The next application of partial fractions is integration. Essentially what happens is you're dealing with an integral involving a rational function of some sort, so a polynomial over a polynomial, but it's too complicated to be able to integrate directly. So we can take advantage of the partial fractions approach to turn our complicated fraction into a bunch of simpler fractions. To begin with, we'll have a bit of a recap. So go back to chapter 1 if you need to and have another quick look at how this works, and then try out these 3 examples. These cover most of the different varieties of partial fractions problems that you might encounter. I'm going to go through each of these in turn to make sure we're familiar with the method, because the main technique you're learning in this section is how to recognize, but then also how to use the partial fractions approach to convert an integral into something that we can deal with directly. The first one, we're going to factorize the denominator to begin with. That's because the entire basis of partial fractions is built from the idea that if you have 2 fractions with different denominators, they can be added together by combining those denominators to give a common denominator. If the denominator we're looking at with this single fraction can be decomposed into separate factors, then there's a good chance we can find 2 separate fractions with those different factors as their denominators that add together to give this fraction. It's important also to notice for this one, we're looking at a proper algebraic fraction. In other words, the order of the top, it's linear, so it's a polynomial of order 1, is strictly less than the order of the bottom, which is quadratic, so it has order 2. So we say that 8 minus x over x times x plus 4 may be identical to some combination of fractions with denominators of x and x plus 4. The next step is to combine those 2 fractions on the right hand side. And you'll notice at this point, crucially, the denominators for the left hand side and the right hand side match perfectly. And if we want these 2 things to be identical, that means they're not just the same for certain values of x, but they are the same for any and all possible values of x. And if the denominators match, then the numerators must match as well. And what that means in practice is that once we know the denominators are the same, we can ignore them and focus on just the numerators. So we've got 8 minus x must be equivalent to a times x add 4 plus b times x. Once we've got that, there's a really useful trick that is probably the most common thing I will do when I'm dealing with partial fractions. There are a couple of different things you can do, and I'll demonstrate both, but this is probably the easiest trick for this standard format of partial fractions. We do what I think of as a savvy substitution. We think of a clever value of x that we can substitute into both sides of our identity and reduce everything down to something nice and simple. In this case, choosing x equals 0 is not just a good idea because it's easy to just get rid of anything where x appears, but crucially, the term involving b is multiplied by x. So if x is 0, b disappears from the equation. We get 8 minus nothing equals a lots of nothing add 4 plus b lots of nothing. Therefore, a is 2. We've got the value of a straight away. If we'd chosen a different value of x, then the equation we generate would still be just as true. We could have x equals 1, and that would give us 7 on the left, and then 5a plus b on the right. And 5a plus b is equal to 7, but then we'd have to come up with another value of x and generate another equation, and then maybe solve simultaneously. What we're doing by choosing x equals 0 is allowing one of our 2 simultaneous equations to be so simple that it only involves one of the variables. And we can actually do the same thing. If you look carefully, we can find a suitable substitution for x that will make the term involving a cancel out. This is the bit involving a. Let's see if we can make that bracket equal to 0. So we set x equal to -4. On the left we get 12. On the right the a term cancels out. We get a times nothing. And then we get b times -4. Therefore we can find the value of b. And that means we can write our fraction now as 8 minus x over x times x plus 4 equals 2 over x plus -3 over x plus 4. I've just replaced a and b with the values that we found. And if you want to double check, it's fairly quick at this point to add the two fractions together and see if you get what you had at the beginning. Another nice way to verify is to pick a random number, preferably one that you've not already tried, something other than 0 and -4, and see what happens when you substitute it into the left-hand side and into the right-hand side. One thing to mention at this point, if you do try substituting in 0 or -4, you'll find something strange happens. The fraction is undefined. That's not a coincidence. It's precisely because those things are factors of the denominator that they turn out to be useful things to substitute into when we were finding terms that fit for the numerator. If it feels a little bit strange using those values to find the a and b values initially, remember all we're doing at that point is focusing on the numerator of each fraction and saying we need these to match for any value of x. And if they match for any value, they will of course match for the two values that we wouldn't actually substitute into the fraction in the first place. But they will also match for all the other ones. So it's really a method for finding the a and b values, which will give us exactly the same a and b values as we'd get subbing anything else in, but more quickly and easily. There's only one other thing I would suggest here. It's probably a little bit nicer to bring out that minus sign and call it 2 over x take away 3 over x plus 4. It's not really essential, but if you've got an awkward fraction on the top of one of those fractions, for instance, add 7 over 2 over x add 4, then it can be a bit nicer to sort that out a bit. Deal with your denominators and numerators so that you end up with a single fraction. It's a little more elegant. Let's look at the second one now. There's a difference here. We have a quadratic on the top instead of something linear, and yet it's still a proper algebraic fraction because on the bottom of the fraction we've got a cubic. So the order of the top is 2 and the order of the bottom is 3. So it's still, effectively, it's like a fraction like 3 over 4. You can't turn it into a mixed number. You can't divide 3 by 4 and get a whole number answer. So this is still going to break apart in a relatively similar way, but there's another important difference. When we factorize the bottom, as you can see, this one's pre-factorized for you, you'll notice that there's a repeated factor. We have x minus 3, and we have another x minus 3. And if it was three completely different factors, x minus 3, x plus 7 or something, we could split it into three different fractions, each of which has one of those factors as its denominator. But when you have a repeated factor, there's a slight difference in the way you set it up. And this is because if you attempted to make this work with b over x minus 3 plus c over x minus 3, well, those two things are basically the same as b plus c over x minus 3. So the whole thing would reduce down and it wouldn't give you enough flexibility. Essentially, we need three distinct constants that we're able to mess with and tweak and adjust in order to make this work. And if the format that we come up with only leaves us with two effectively different constants, then we're not going to be able to break apart the fraction. You don't need to worry too much about the ins and outs, but if you want to play around with it and try to see what happens if you come up with a different approach, then by all means do so. The method we're going to apply here is the same kind of thing we did before. So we need to add the fractions on the right and generate a common denominator. The common denominator on the right should perfectly match the denominator on the left. So you can see that the first fraction, a over x, needs multiplying by x minus 3 squared over x minus 3 squared. In other words, times the top by x minus 3 squared and times the bottom by x minus 3 squared. That way the denominator will match the one on the left hand side. For b, you need to multiply the top and bottom of that fraction by x and also by another x minus 3. And when we get to c, we just need to multiply the top and bottom by x. You'll notice also one slight time saver. I'm not writing out the denominator. I could, but I know what it would be. It will be x times x minus 3 squared, and more importantly, I know it will be the same on the left-hand side and the right-hand side. So it's not strictly necessary to write it out on both sides if all we're going to do is ignore it from now on. We're going to use the quadratic on the left and the quadratic on the right, and we're going to compare them and figure out what a, b, and c would have to be to make this work. Now we can do a similar thing to what we did before. We can think of a savvy substitution. Is there a value of x we could substitute in that would allow certain things in here to cancel out nicely? And x equals 0 works quite nicely again because x is a factor. In fact, x is a factor of both this bit and this bit. b times x minus 3 and c times x. So both of those will cancel out. And we're left with just minus 9 equals a times 9. So a is equal to negative 1. The next logical substitution to make is x equals 3. And in this case, if we set x equal to 3, we find we can cancel out the a bit because there's an x minus 3 bracket there. And we cancel out the b part again. And we're left with just the c component. And that means we can calculate c. Everything else disappears, cancels down, and we get c equals 1. But you might have noticed the problem here. There is a way to cancel out a and b. There is a way to cancel out b and c. There is no way to cancel out a and c without also cancelling out b. Anything that cancels c will cancel b, and anything that cancels a will cancel b. If you want to not cancel b, you have to not use 0 or 3. But if you don't use 0 or 3, you won't cancel out a and c. Well, this isn't as big a problem as you might think, because although these were the most efficient and lazy substitutions we could come up with, they are only 2 of an infinite number of perfectly valid substitutions. We can put any number we like in instead of x. And even if we get something that doesn't perfectly cancel out everything, even if it involves a and b and c, that's not a problem necessarily. Importantly, because we already know a and c. So even if we got an equation with a, b, and c in it, it still doesn't stop us from finding the value of b. So let's try x equals 1. It's a nice, easy option. On the left-hand side, we have 1 squared, add 1 minus 9. And on the right-hand side, we will have 4a minus 2b and c. Well, if we put all that together, remember we can rearrange this and we can substitute in the values that we already have. We know what a is and we know what c is. So we can make use of those and simplify and solve for b. Now we've got the value of b. The last thing to do is to go back to our original fraction and rewrite with the appropriate values a, b, and c in their appropriate places. The third example is a little bit different. The numerator has a cubic, a polynomial of order 3, and the denominator is a quadratic, a polynomial of order 2. So this one is most definitely a top-heavy fraction, an improper algebraic fraction. The first thing I would think about when looking at one of these is the kind of answer you would expect to get if you were to carry out the division that's implied by the fraction. If you start with something cubic and divide by something quadratic, what kind of answer should you get? The easiest way to make sense of this in your head is to think of the simplest cubic and the simplest quadratic you can. If you do x cubed and you divide it by x squared, you get x, which is linear. And that's true for any cubic and any quadratic. If you divide a cubic by a quadratic, you get something linear. In fact, if you divide anything of order, say 7, by something of order 3, you will get something of order 4 as your quotient, your result. There may be a remainder as well, but the bit that we're most interested in here is the quotient, the bit you get, which doesn't have any division going on inside it. So this is the kind of thing we're going to end up with. If we're able to break apart a cubic divided by a quadratic, it should end up giving us something linear, which I've called ax plus b, and then the rest of it could then be broken down in the normal way, because the rest of it will be a proper fraction. That's the whole definition of algebraic division. You're taking something which is an improper fraction and you're rewriting it in a form that involves a polynomial, the quotient, plus a remainder over the divisor. In other words, something over, in this case, x minus 1. And that remainder must have a lower order than the divisor itself, because it's a proper fraction and the divisor is its denominator. So if the divisor is quadratic, then the remainder must be at most linear. We've got something linear over something quadratic, which is exactly the same as the very first example that we did back up here. So we can break it apart in the same way, and we'll get something like this. Let's see how this works. We can still add the 4 terms on the right hand side. 2 of them don't look like fractions at all. We can think of ax plus b as being a single term if you like, as I've done here, stick it in brackets, but we're going to multiply it by x and by x minus 1, because at the same time we're dividing it by x and x minus 1, so that all of those terms on the right share a common denominator, x minus 1. C gets multiplied by x minus 1, as well as being divided by x minus 1, and d will be multiplied by x over x. Then all the denominators match, and we can ignore the denominators and just look at the numerators. Now, how do we break this one apart? Well, we do the logical things. We try substituting in things that will make stuff cancel. There is a factor in here. There's an x that we can make use of, which multiplies by the ax plus b term, but also by the d term. So if we substitute that in, everything apart from c will cancel out. And that's what happens. We can find the value of c. The next logical thing to try is 1. If we substitute x equals 1 into our formula, it'll cancel out this bracket and this bracket, and we'll be able to find the value of d. We get minus 4. Then it gets a little messy. So there's nothing else we can substitute in that won't cancel out the thing that we're trying to find. We need to find a and b. So let's try substituting in a couple more values of x. We pick nice simple ones. If we've not already used 0 or 1, we would use those. And if not those, then the next logical options are minus 1, 2, things like that. So I'm subbing in minus 1 to see what we get. And as expected, we get something which involves a, b, c, and d. But remember, we already know c and d. We've got numbers for those. So wherever you see c or d, we can just replace them with the appropriate numbers. And when we perform the substitution, do a little bit of simplifying, we get 2a minus 2b equals 2. I won't simplify that, I'll leave it in that form for now, because if we're going to be solving it simultaneously in a minute, we don't know what the most appropriate form might be. The next thing we'll need to do is the same kind of thing again. Pick a value for x. There's no right or wrong answer here. Just choose a number that you are happy substituting into both sides and think you're less likely to make mistakes with. I've gone with 2, excitingly enough. And we end up with 4a plus 2b plus c plus 2d is equal to minus 1. That cancels down, simplifies a little bit as well. We get 4a plus 2b equals 4. Now you could at this point cancel down, write both of those in a more straightforward format, but in their current form it's easy to see how we can solve those simultaneously anyway. You could do it with a calculator if you wanted, and if you do end up with 3 simultaneous equations in 3 unknowns, which is also possible with some of these depending on your method, then you might find it's a lot quicker to take advantage of your calculator, which I believe can work things out up to and including 4 simultaneous equations in 4 unknowns, which might be quite handy. But in this case, it's pretty easy to deal with using elimination. If you add the left-hand sides, you get 6a. If you add the right-hand sides, you get 6. So a is 1. If, on the other hand, you double the top one, or equivalently halve the bottom one, then you could subtract one from the other and you could find the value of a. Or you can use substitution once you know the value of b. Find the value of b. Anyway, whichever way around you do it, you should get a equals 1, b equals 0. And you can double check that they work by substituting them in. We get 2 times 1 take away nothing is 2, and 4 times 1 add nothing is 4. But that seems a little bit much. Those last 2 steps, they weren't particularly quick and simple. There were all sorts of little places where you might make a mistake. I certainly did. I made a couple of different mistakes when I was going through this the first time through. I had to keep going back and correct it. There's a lot of little things going on, and that's often the place where little mistakes can creep in and be hard to notice. There is an alternative method. The previous method felt a little bit clunky and slow towards the end, so this seems like a good opportunity to demonstrate the alternative. We still do the first couple of lines the same, but now we're going to see what happens if we use the comparing coefficients approach. This approach is essentially saying, If you've got a quadratic and I've got a quadratic, and we think they're identical for any and all values of x, then the number of x squareds needs to be the same, the number of x's needs to be the same, and the constants at the end need to be the same. Exactly the same principle we're using here. We have a cubic, so we can compare in turn the x cubed terms, the x squared terms, the x terms, and the constants. We start by looking at the x cubed terms. And somehow I've just jumped to 1 equals a. Where did that come from? Well, let's have a look. On the left, the x cubed term is just 1x cubed. On the right, we can find an x cubed term by multiplying ax by x by x. And if you look carefully, you'll find that's the only place you can find an x cubed term. B is just a constant in that bracket. The most you can get from that is bx squared. If you were to expand that out, you get a bx squared and a bx times minus 1. You wouldn't get a bx cubed anywhere. And the c and d terms, they're just multiplied by something linear, so there's no way they're going to contribute anything to the x cubed terms. So we know straight away the value of a. We can do a similar thing with the x squared terms. If we look closely, we have a negative x squared on the left, and on the right hand side, we need to be a little more careful here. There's a couple of ways to get an x squared term on the right. We can have ax times x times minus 1. But we can also have b times x. So if we put those together, and we notice that they are the only places you can get an x squared term, we can calculate b. Remember, although we have just an equation involving a and b, we already know a, so you can sub it in and find b directly. What about the x terms? Well, if we look for those, got a minus x on the left. On the right hand side, there's quite a few places you might get an x term, but not as many perhaps as you might think. In the big term at the beginning with the ax plus b, you'll notice that everything gets multiplied by x in there. So you won't have any constants coming out of that, but also there won't be much in the way of x terms. To get an x term, you would have to have b times x times minus 1. That's the only way it can happen. Because everything will be multiplied by x, you need everything else to be constant. So there'll be a minus bx squared. Sorry, minus bx. And then in addition to that, we'll have cx and we'll have dx. So we get a minus b, a c, and a d, balancing a minus 1. Remember, we know b, so we now have a link between c and d. Not enough on its own, but if we include the constant comparison, we can presumably find both c and d. And it turns out the constant terms, the only thing that provides a constant term is c. So minus 3 is the constant on the left, and if we do c times minus 1, that will give us a constant on the right. Nothing else provides a constant. Once you know c, you can go back up to the equation above and use it to find d. And we get the same result. We've got the same values for a, b, c, and d as we did before, but you might feel like this is a slightly more efficient approach in this particular case. In actual fact, neither of these, I think, is the very best way, but generally a blend of the two is the most efficient approach. So what I'd suggest is you either choose wise substitutions that will make things cancel out nicely, but then when you run out of nice things to substitute, then think about the coefficients involved and see if you can pull anything out usefully by looking at the x cubed terms on each side and so on. Very often the things that yield most easily to the savvy substitution alternative are the things that are hardest to get by comparing coefficients, and vice versa. So these two methods complement each other quite nicely. If you're feeling a little bit rusty on the entire process of partial fractions, if it feels like it's been a very long time since you learnt it, I highly recommend going back to chapter 1, trying a couple of mixed exercise questions on these, get your hand back in without having to think too hard about integration at the same time. Focus on each bit, then when you pull it together at the end, it'll feel fairly natural and easy to do. So where does integration come in? What's the value of breaking apart these fractions? It takes quite a bit of work, even if you use the most efficient methods. So why do we bother doing it? Well, let's look at a couple of integration techniques we already have that deal with fractions. Here's one of them. It may not look like it deals with fractions. Ax plus b to the power n. You might think of it as a method for dealing with the square of a linear term, or 7x minus 9 to the power 4. But also, we can deal with things like n equals minus 2. You've got a fraction with something squared on the bottom. Here's a few examples. Each of these is something which can be dealt with using the rule above. You just need to find the right way of writing it, so choose an appropriate index form so you can get the right value of n, and then don't forget, when you integrate, you treat that bracket as if it's a single term effectively. We have increased the power by 1 and divide by the new power. That's why this n plus 1 is here and why this n plus 1 is here. But in addition to dividing by the new power, we also have this ax plus b on the top gives us the a on the bottom, the derivative of the bracket. This is essentially reverse chain rule, remember. So if you were differentiating a bracket to a power, you would bring the power down in front, reduce the power by 1, and then multiply by the derivative of the bracket. And if it's something linear, the derivative is a number, just a constant. When we integrate terms like that, we can reverse the process because it's just pulling out that constant from the integral sign. Have a go at these, see if you can get these answers, and then we'll go through them together. Okay, here's the first one. By rewriting the bracket with a power of minus 2, we can turn it into 3x minus 4 to the power of minus 1 divided by minus 1. We also remember to divide by 3, the derivative of 3x minus 4. We still have the 7 kicking around. That just stays there at the front, and it shouldn't bother us. We can leave it in that form, but things like 3 times minus 1 should be simplified. It's not usually done to leave a negative on the bottom of a fraction. And you certainly shouldn't leave things like 3 times minus 1 unsimplified. The other thing that you might want to do is change that 3x minus 4 to the minus 1 into a fraction again. So we turn it back into 1 over 3x minus 4. The next one involves a power of minus 3. So the 5 on the top and the 2 on the bottom have been pulled out in front to be a single constant that sits around all the way through and doesn't get in the way. Then increase the power by 1, divide by the new power, changes a minus 3 to a minus 2. We divide by the minus 2. If the derivative of x add 6 had been anything other than 1, we would have divided by that as well. Since it's 1, dividing by it and not dividing by it do the same thing. So I've not included a 1 down there. The final step is to sort out those fractions. 5 over 2 over minus 2 is minus 5 over 4. So I've left a 5, a minus 5 in fact, on the numerator, and I've collected together the 2's on the bottom. Another way to think of this step is multiplying the entire fraction, the big fraction, by 2 over 2. If you multiply the top by 2 and the bottom by 2, in fact by minus 2 in this case because I'm sorting out the negative at the same time, if you multiply the top and bottom by minus 2, 5 over 2 becomes minus 5 and negative 2 becomes 4. And that deals with the denominator of that fraction that was in the numerator before. The only other thing I've done is changed our x add 6 to the minus 2 into 1 over x add 6 squared. Now the last one looks a bit different, and yes, you're less likely to come across this particular sort doing partial fractions, but it's worth throwing it in there because it does often look quite different to students. You've got the fraction involved and a square root, which can make it harder to recognize that this is actually exactly the same type. Something linear raised to a power. So we can increase the power by 1, divide by the new power, and hopefully you can spot the mistake on this slide. Something that we did for the first example, something that we didn't need to do for the second example, and therefore got cocky and forgot about for the third example. When we divide by the new power, we don't just divide by the new power, we also divide by the derivative of the bracket. And therefore, when we sort all of that out, in fact, the 2 times the 3 over 2 sorts out the bottom, and we just get a 3 there as before. But instead of an 8 at the end, we should have a 4 in there. So well done if you got all of those. Here's the next technique. This one looks more sophisticated, but it's probably the nicest. It's really quick to do once you start to learn how to spot these. And they come in a whole wide range of different formats, but there's just a handful that you're likely to come across when dealing with partial fractions. and they're really useful to be familiar with and confident with. So have a go at these ones and see if you can identify how these can make use of that idea. If the top of a fraction is the derivative of the bottom, then the integral will be ln of the bottom. Give them a go. When you're ready, continue the video. So the first one, I'm going to pull out that 7, but I'm also going to pull out a 1/3 that wasn't there in the first place. The only reason I'm allowed to do that is because I'm also multiplying by 3. So you can think of this as being introducing a 1/3 of 3 term. I'm multiplying by 1, I'm calling it 3 over 3, I'm leaving one of the 3's in the fraction, I'm pulling the other 3, the over 3 bit, outside the fraction, so that I can ignore the 7/3 and focus on the bit within this integral which perfectly matches the rule. The top is the derivative of the bottom. 3 is the derivative of 3x minus 4. So now when I integrate, I can use the rule. 3 over 3x minus 4 integrates to ln 3x minus 4. And we still have the 7/3 out front from before. The next one, we need to look carefully and think about what the derivative of the bottom is. X squared add 8 differentiates to 2x. And we've got 5x on the top. So what I'm going to do is pull out the 5, so it's just an 1x on top, and then I'll double it to make it 2x, but to compensate I will also halve it to make it 5 over 2 times 2x. And the reason we do that, again, is so that this fraction perfectly matches the format that we're looking for, and we get ln of the denominator. With the last one, it almost matches again, but in this case, x squared minus 4x differentiates to 2x minus 4. We've only got 1x minus 2. So I'm going to double the numerator so that it matches. But in order to do that, I had to also halve, otherwise the integral would not be equal to the original integral. And the final result will therefore be half of ln of the denominator. So these are those two rules again. I recommend you jot these down and you look carefully at the little examples that go with them. The most common format that you'll find when you're dealing with partial fractions questions and you need to use these rules, things like 2 over 3x add 4 in a bracket squared, or 2 over 3x add 4. They may look very similar, those two examples, but they're quite different under the hood because one of them involves the bracket to a power inspection rule, and the other one involves the top as the derivative of the bottom log rule. So make sure you're familiar with those. You recognize if it's just something linear on the bottom of the fraction, then you're going to be using the log rule. If it's something quadratic, then hopefully you can make use of the power of something linear inspection rule above. If you want to practice with these techniques a little bit more before you dive into putting everything together, then exercise 11b question 3 has got some good questions. It has a mixture of fractions with a single linear term on the bottom and fractions where you've got something squared or even cubed on the bottom. Now let's see if we can put both of these things together. Partial fractions methods along with the integration of fractions. We take something big and complicated that we can't directly integrate, we split it using the partial fractions technique, and then we generate something which can be integrated. So let's see what happens when we apply this to the previous examples. We already worked through these 3 questions, but we didn't do them as integrals. We just looked at the expression inside and we split them into partial fractions. So if you want to look back at your notes, you can find those results. If not, go back to the early bit of the video, you'll see how they are split into partial fractions once more. I'm going to use that result because we already know that 8 minus x over x squared add 4x is equivalent to 2 over x minus 3 over x add 4. And we know that 2 over x integrates to 2 lots of ln x. If you like, you can think of it as 2 times 1 over x, and we know what 1 over x integrates to. For the next one, 3 over x plus 4, it's a similar sort of idea. If you're a bit concerned about the x plus 4 and why that behaves in the same way, you can think of the top as the derivative of the bottom method, because the derivative of x add 4 is just 1. So if you have 1 over x add 4, the integral will always be ln of x add 4. For the next one, when we break into partial fractions, we got minus 1 over x, plus 2 over x minus 3, and plus 1 over x minus 3 squared. So with this one, we've got logs for the first two terms. We have minus ln x, and then plus 2 lots of ln x minus 3. But then the next term involves the first of those two integration results, ax plus b to the n. We can think of that part as x minus 3 to the power of minus 2. Increase the power by 1, divide by the new power. That's why we have a power of minus 1, and that's why a negative sign has appeared. We also divide by the derivative of whatever's inside, but since what was inside was just x minus 3, the derivative is 1, so nothing else happens there. For the final one, remember we had a bit more work to do with this one, but we can end up breaking it apart into x plus 3 over x minus 4 over x minus 1. So the first bit is just a polynomial. In fact, it's a really simple one. It's just something linear. It's x itself. We can integrate that using the standard results. X becomes x squared over 2. The next two bits end up breaking apart into logs. And it's worth noticing at this point, if you wanted to simplify those two logs, you could. You can make use of the log laws. 3 ln x is the same as ln of x cubed. 4 ln x minus 1 is the same as ln of x minus 1 to the 4. And if you have ln of something minus ln of something else, then you can combine them by dividing the two inner terms. ln a minus ln b is just ln of a over b. And sometimes it's helpful to be able to put your logs together, but it's not essential, so you're perfectly at liberty to leave your results in this format like I have here. Now you can have a go at the first question from exercise 11G. Next, I want to look at another example. This one's also taken from 11G, but this is question 4. There's quite a few things going on with this one. For a start, they've asked you to integrate, and you're going to need to figure out how to do that. Secondly, when you realize you've got partial fractions involved, you can see it's not a particularly basic one because you have a repeated factor on the bottom. And thirdly, it's a definite integral, which means there are limits that you need to put into that. Remember the rules for partial fractions. We can do either of these two things, either substitute numbers, or we can compare coefficients, or we can do a mixture depending on what works out the best. And when it comes to integrating, we've got two main results that we'll be relying on during this topic. One of them is something linear raised to a power, and the other one is when the top is the derivative of the bottom. So let's dive in and give it a go. The very first thing we need to do is recognize that we can't deal with it in its current form, so we're going to break it apart into simpler pieces that we can deal with. So let's ignore the integral and focus on the expression inside. We split that into something over 3 add 2x, something over 2 minus x, and something over 2 minus x squared. Remember that repeated factor, 2 minus x squared, that needs to be dealt with by having a bit over just one copy of the bracket plus something over the squared copy of the bracket. Next, you can think of this in two ways. You could think of it as adding the fractions on the right and then only comparing the numerators, or you could think of it as multiplying through both sides by the denominator. The effect is the same. What we end up with is a times 2 minus x squared, because that was what was missing from the denominator of that first fraction. And then b needs one of the 3 plus 2x brackets, but it also needs a second of the 2 minus x brackets. C has 2 minus x squared, so all it needs is a 3 plus 2x. When you've got all of those, then you want to start thinking about how you're going to reduce things, simplify things down, and find out what A, B, and C are. Before you dive into expanding out brackets and rearranging terms, notice that there's quite a lot of different terms here. And it's worth thinking about what you intend to do and why before you plow ahead with some technique that's going to take you a while and may end up causing mistakes along the way to boot. So remember, substituting wisely is the laziest and therefore the most efficient method for this. If we can put in x equals 2, for instance, look at what happens. A whole bunch of things cancel out. When x is 2, 2 minus x is 0. So anywhere where you find a 2 minus x will disappear. And on the left-hand side, you can substitute in 2 and you get 7. On the right-hand side, when you substitute in 2, the only bit that doesn't cancel out is c times 7. so c is 1. We can do a similar thing with minus 3 over 2. A bit less obvious, but remember you're concentrating on what will make this bracket disappear. So what if 3 add 2x is 0? We'd need 2x to be minus 3, so we need x to be minus 3 over 2. Setting x to be minus 3 over 2 allows those bits to disappear entirely, so the b component and the c component no longer exist, and we're left with just a times 2 minus 3 over 2 squared, and on the left 17 take away 5 lots of minus 3 over 2. So the fractions are a little messy, but nothing you can't deal with. We get a equals 2. And the next part, I've decided that because I only need one more thing, I'm not going to start comparing coefficients. I'm just going to jump straight to let's put in x equals 0. It'll be relatively quick, and I already know the values of c and a. So if x is 0, the left-hand side reduces to 17. The right-hand side, a, b, and c, all of them appear somewhere. But you'll notice it's pretty quick to substitute in 0. When I'm reading the b section, for instance, I read it as b times 3 times 2. Because anything that has plus 2x or minus x, I'm just adding nothing. And then c times 3, a times 2 squared. When we substitute in the values for a and c, 2 and 1, then this immediately gives us a value for b. Once we've got all of them, we can then write out our partial fractions version of the original expression. And we've done the first part. Arguably, this is the longest bit. Breaking into partial fractions is the tricky part. When you've done that, it's a case of following the routine procedures that we've got in the top right for integrating these sorts of expressions. So here's how we integrate. We look at each term in turn. Notice each of the three fractions is separate. It's a separate term in the sense that they're added together. So you can integrate each one separately and add the results. Take them one at a time. The first one, for instance, 2 over 3 add 2x. Well, fortunately for us, the derivative of 3 add 2x is 2. So that one perfectly matches the appropriate format. We're going to get ln of the denominator. The next one almost matches. The denominator is 2 minus x, so the derivative is minus 1. So we'll need a minus 1 on top. Well, all we need to do is change the 1 to a minus 1 and change the plus to a minus. And then we're sorted. That now matches the format. For the last of the terms, it's not one of the log rules at all. It's the one above. You can think of it as 2 minus x to the power of minus 2. So we should get something like this. ln of 3 add 2x, because the top is exactly the derivative of the bottom. We get minus ln of 2 minus x, because the top is the derivative of the bottom provided we change the sign. And then the last bit, two things have happened. There is a change of sign, but there is another change of sign as well. So 2 minus x to the minus 2 integrates to 2 minus x to the minus 1 over minus 1, and also divided by the derivative of 2 minus x, which is also minus 1. So there's a couple of minus 1s appearing there and annihilating one another. But the final bit of this was substituting in values. So we're not just integrating, we're integrating between 0 and 1. And remember, now you're dealing with more complicated functions than just polynomials. Substituting in 0 very rarely gives you 0. So watch out for that. Put it in properly. Don't just assume that you're taking away nothing at all. We'll do ln of 3 plus 2 1s, take away ln of 2 minus 1, plus 1 over 2 minus 1. And then we do the same thing but putting in 0, and we subtract 1 from the other. You might notice ln of 1 is equal to 0, but even if you don't notice that, when you start combining and simplifying the logs, then that will disappear anyway. For instance, we know that ln of a minus ln of b is ln of a over b. So ln 5 minus ln 1 is just ln of 5 over 1, which is the same as ln 5. What else can we do? Well, be careful with your brackets, but we're taking away ln 3 and we're adding ln 2. You can combine your logs in any way you like, but you'll probably find it easiest to separate out and deal with those brackets first and then combine the logs. So I've got rid of the brackets. I have a half, that's the 1 minus the half, and then we have ln 5, ln 2 minus ln 3, and I've ignored the ln 1 because ln 1 is 0. When you put those logs together, we multiply the 5 and the 2 and we divide by the 3, because that's how the log rules tell us to do it. You should be able to have a go at questions 3 and 6 now from exercise 11G. They should be fairly suitable for where we're up to right now. Now I've just got one more example I want to go through with you. This last example has a top-heavy or improper fraction involved. So it's going to take a little bit longer to break apart into partial fractions. But if we already know what we're expecting, then that's going to help a lot. We have x to the power 4 on the top and a quadratic x had 1 times x had 2 on the bottom. If you divide a polynomial of order 4 by a polynomial of order 2, the quotient, the result of the division, will be a polynomial of order 2. Just like x to the 4 divided by x squared will give x squared. The remainder will be something which is strictly lower order than the denominator, which means it can't be any more complicated than something linear. And that bit could be broken into partial fractions just by having a over x plus 1 add b over x plus 2, for instance. So all that remains is to figure out what that quadratic quotient would be that we deal with at the start. The quadratic quotient could be written as ax squared plus bx plus c, and I've written the final part as d over x plus 1 add e over x plus 2. Now, if you have got a quick and efficient algebraic division method, then I'd recommend you have a go at using that. You might want to expand out the x add 1 x plus 2 and then divide directly, see what you get for your quotient, and that will give you the a, b and c values. It will also give you a remainder which will tell you what you would have left over on top of x add 1 x add 2, and breaking that apart would tell you the final two pieces of the puzzle. But I'm going to show you a method which uses exactly the same results we've been doing so far, and you should find it's pretty similar in terms of how much you've got to do. And again, it's going to really take its power from a combination of both savvy substitution and comparing of coefficients. So let's start by doing the usual thing. Let's multiply both sides by the denominator, or equivalently add together the terms on the right hand side by finding a common denominator, which incidentally will match that on the left, and then we'll compare the numerators. However you want to think about it, what you'll find is we get some big complicated term at the start, ax squared add bx add c multiplied by the entire denominator from the left, and then the d and the e bits are going to be a little bit simpler. Now, the savvy substitution we're talking about will involve, for instance, x equals minus 1. You can hopefully see which bracket that's going to help us with. If x is minus 1, then anything involving x plus 1 will immediately cancel out and disappear, leaving us with d being the only term that still remains. We'll have d times minus 1 add 2, in other words, just d times 1 on the right hand side. And on the left, we've got minus 1 to the power 4, which is also 1. So d is 1. The next substitution we're going to make, it would make sense here to deal with the x add 2 bracket. We'll make x equal to something which makes that 0. So if x is minus 2, then we can find the value of e. That's the only bit that doesn't disappear when we substitute x equals minus 2 into the identity. But at this point, we get a bit stuck. We could start substituting other things in, but it's a big, long expression on the right-hand side, and I would prefer to find a lazier approach. So this is where I switch across from substituting to comparing coefficients. I'm going to have a look at the largest ones first, partly because I've already got d and e. They were the ones that fell out most easily from my substitutions. The a, b and c terms will be the ones that require looking at the other end of the spectrum. Where do we get the x to the 4 term? Where do we get the x cubed term from? Well, you can probably already see where x to the 4 is going to come from. There's only one place you can get a term with an order of x as high as that. We'd need ax squared times x times x. So as soon as we compare the coefficients for that, it should sort itself out. Now you might find it a little bit easier to rewrite slightly. I've still not expanded out the whole thing, but this is what happens if we expand out the x add 1 x plus 2 brackets. So this piece here can be turned into this. So it's a little more readily apparent for the a and the b and the c where each of those will combine to give various different terms. And I've done a similar sort of thing for the d and the e bits. So for each of those, I've had a look at can we write them in terms of the x components and the constants. That'll make things a little bit quicker if we get that far. Those constant bits, in fact, we don't really care about, and the x bit we don't care about because we already know d and e. But for the sake of completeness, I've sorted those out a little bit as well. Now let's take a look at the x to the 4 coefficient. You can see that the only thing that gives an x to the 4 is ax squared times x squared. Now the x cubed coefficient can come from a couple of different places. So if we look carefully, we'll find ax squared times x, or 3x in this case, so that gives 3a, but also there's a bx times x squared. That will also give an x cubed term. But on the left, there are no x cubed terms, so the total of the x cubed coefficients on the right-hand side has to be 0. And since we already know the value of a, that gives us the value for b. And the last thing we need to look at here is the x squared terms. Those will come from a couple of places. Ax squared times 2, bx times 3x, and c times x squared. So even that one isn't too much work. And remember, we already know a and we already know b, so it's just a case of substituting those numbers in, and out pops c equals 7. Once we've got that, we've got the thing we need to integrate. So we rewrite it in its partial fractions form. There is a quadratic at the beginning, so that polynomial at the very front is going to be nice and easy to integrate directly, and then the next two terms will yield to the log trick just above, because in each case it's just a single linear term on the bottom of a fraction. So the derivative of a linear term is always constant, and we can always adapt the constants to make them work the way we want. In this case, the derivative of x add 1 and the derivative of x add 2, they're both 1. So as long as we can make the numerator 1, we'll just pull out any other constant from the integral. We can sort it out pretty quickly. X squared becomes x cubed over 3, minus 3x becomes minus 3x squared over 2, 7 becomes 7x, 1 over x add 1 perfectly matches the result above, so we get ln of x add 1. And if we pull out the minus 16, we're left with 1 over x add 2, and that gives us the same kind of result, ln of x add 2. If you wanted to, I've shown here how you could combine those logs, but it's not generally much quicker or easier or nicer. So unless you're asked specifically to write your answer in the form a plus b ln x or something like that, or write your answer in terms of a single logarithm is sometimes how they write things, it's not usually necessary to turn your expression into something at a particular form. Now you should be able to have a go at questions 2, 5 and 7 from exercise 11G. Happy partial fractioning.